there you go. So I will have this talk on the life cycle assessment as a tool for the measurement of environmental impact. So my name is Beaucamp Loughlin. I'm an academic here in the University of Limerick. Our university is based in Ireland. We're about 15,000 students, about 3,000, 4,000 staff. So quite a young university here, where it rains a lot. So that water ecotoxicity was quite interesting. So I want to start this talk with explaining what is the life cycle assessment. So to do a life cycle assessment, our goal is to look at the impacts of the environment associated with the full life cycle of a product, process, and service. So we're looking at each part of the life cycle. So from materials extraction, raw material extraction, to transport, manufacturing, distribution, use, all the way to disposal and recycling. And we're looking at all the possibilities that there are to reuse, to repair, and to recycle and re-inject some raw material inside the system. So this is a solution that allows for the quantitative evaluation of inputs, outputs, and potential environmental impacts of a production system through its life cycle. So it's quite a strong tool. So sorry, yeah, there you go. So as per the stages of the LCA are per the ISO 14040 that was edited in 2006. So there are 4 stages: the goal and scope definition, the inventory analysis, the impact assessment, and finally the interpretation. And the application, the direct application of these methods are to allow for the product development and improvement, strategic planning, public policy making, marketing, and other. So the 4 stages are: the first one, goal and scope. So we are defining the functional unit, the system boundaries, and the methodology. In the second one, the inventory, we're gathering all the inputs and outputs for the processes within the system boundaries that were defined previously. The impact assessment characterizes those input and outputs according to damage potential or impacts. So we'll get to that later, but this is, for example, to amount the emissions of carbon dioxide, for example, would be one of those impact indicators. And finally, we interpret. So to interpret, we have to normalize, weight, and analyze all the contributions, and also do sensitivity analysis to be sure that our LCA is robust enough. So when it comes to the goal and scope, so we have first to define a functional unit. So that functional unit is a quantified description of the function of a product that serves as a reference basis for all calculations. So a lot of the functional units for the studies that we did for Bio-Uptake would be linked to 1 kg of bio-based material, 1 kg of bio pellets, for example. But sometimes we had to use functional units that were closer to a batch. So production of a batch of bio pellets over 8 hours of extrusion, for example. The boundaries are indicating the limits of the system that we investigate using the LCA method. So basically, they're telling us where we start and where we stop. So the largest, the full life cycle is a cradle to cradle, where we're going from resource extraction all the way to resource reimplementation. And the shortest one would be cradle to gate, where we go from resources to transport for the manufacturing place. And we have cradle to grave as well, which goes from resource to disposal. So the life cycle assessment that I'm going to be presenting forward are cradle to gate. So to collect that data, what we had to do was to send inventories to the partners, inventory questionnaires. So those would help us establishing the functional unit and also the input and outputs. So we used all the data that was shared by the partners, and if there were any gaps, we used databases such as EcoInvent, for example, and literature as well to help us fill those gaps. So the type of data that was obtained from the partners would have been materials flows, so amounts of materials, amount of waste, the energy that is used, the amount of utilities such as water, water input and wastewater, but also if they were used for any gas such as nitrogen or argon during the processes, all of those would be amounted. And once we have our goal and scope, so we looked at the impact categories. So we're working in Europe, we're working with a methodology called environmental footprint EF, and we're at the version 3.1 at the moment. So that methodology goes through 16 impact categories, the most known of which would be climate change, which is expressed in kg CO2. But you also have water use, land use, acidification, ozone depletion, human toxicity, eutrophication, ecotoxicity for fresh water, human toxicity, cancer. We have resource use, fossils and minerals and metals, particulate matter, freshwater eutrophication, terrestrial eutrophication, ionized radiation, and photochemical ozone formation. So this is quite a large panel of environmental indicators that are tested here. So those bio-based Bio-Uptake products, so you've seen a flowchart previously. So we basically looked at that flowchart again and redid it. So we had the partners that provided us with the data. So Centexbel provided us with data on the PLA and PCL producing into filament yards that were then sent to Comfill here to make UD tapes and organosheets. SP provided data on the cans, and we had Moses who provided data on the pellet extrusion compounding and then over injection into the lids for the garbage container. The cans were used with bio-epoxy to make the endured organosheets using flax fibers, and they were then thermoformed in Beaucamp to make the sealing of the bathroom pods. And finally, for the feet installed, so we had Centexbel work into the filament yarns for the organosheet, and then the UD tape as well for thermoforming. So those were quite complex systems, and as you can see, all the partners basically had input. And the other thing to say about that is that every system was very much interlinked. So if one partner made a different change in one system, it was basically impacted the full value change. So just to give you an example of a Centexbel system model, we went from raw material, distribution of the raw material to the 4 polymers that were tested for the project. So we had a low melting point PLA, a high melting point PLA, a polycaprolactone, and the polypropylene for rinsing. The 3 PLA, the 2 PLAs and the PCL went into the dryer for drying, then melt spinning, and they then produced the filament yarn here. There were also, we considered the waste for cleaning and the production waste. So you see the amounts 1.5 kg per run and 0.3 kg per run, and then the end of life consideration for those waste. And the filament yarn itself was sent for the organosheet. So in each we had input of electricity and heat, and where needed water as well. Sorry, up. There you go. So when you look at the impact presentations, so this is where we would look at the values. So we have the impacts that are represented in single score in millipoints here, and each impact would be represented as a part of a bar chart. So this is gone through normalizing and weighing, which is done within the methodology that we're using. So as you can see, the three PLAs that were used are quite similar in terms of impact, while the PCL has a higher impact. And this impact is higher across, mostly across all categories, slightly lesser on climate change. So in our case, we focused on climate change as an environmental factor, but also at resource use fossil. And the last thing that we looked at was the use of energy. So we went into further analysis by looking at which, basically which part of the process was the highest contributor to our environmental impact. So for the case of this PLA, the largest contributor is actually the resourcing of raw material. So making the PLA itself. The manufacturing and the distribution were quite low. So manufacturing here would be all the energy that is used, or all the impact of the actual extrusion. So if I move now to the Moses model, so we have quite a similar model with raw materials, distribution, and the two polyamides, the wood dust, and the biofibers. So we had the extrusion compounding and the reinforced biopellets as an output. And as you can see, and it's quite similar to what was found in mechanical as well, the polyamide 11 has quite a higher, smally higher impact than the polyamide 1010. And as it was mentioned, the polyamide 1010 reinforced with recycled carbon fibers has a higher impact than the recycled wood. This is mostly due to the fact that even if they're recycled, those carbon fibers were recycled using a pyrolysis process, which is quite energy demanding, and it had a large impact finally on the overall product. So doing this, we basically the project continued with the recycling wood polyamide 1010 and the polyamide 1010 with a 5% carbon fibers, as we try to reduce as much as possible the impact of the carbon fiber. So when it comes to the recycling wood, the impact contribution mostly came to the supply of the PA 1010 and the mill spinning process. So we're continuing with this. We're now looking into the assembling of that product model. So we're basically putting together all the intermediate formats to continue with the modeling. And we're looking at going beyond the cradle to gate. So we're looking at the evaluation of the use phase impact based on the data I've shared with the partners. So this is done with the data that was gathered by University of Aveiro by Isabel. And we're looking into the end of life processes as well, which are currently being worked on by the partners in Moses. And finally, we're comparing those with the benchmark. So to take home, this is a standardized, systematic, and quantitative method which allows for the evaluation of the environmental impact of a process, or service through its entire life cycle. It allows us to make informed decision on the design of a product early in its conception and production process. And it also highlights hotspots in the production of a material, allowing for earlier remediation where possible. So this is it for me. We can have a short FAQ if there is any questions. I don't see any in the chat. Yeah. I think I'm waiting for a few minutes, Isabel, but we may be off the hook on this one. Okay. Well, I think we stop there in that case. Yeah. Okay. So thank you everybody for attending us today. This was, I hope that, I hope that this webinar was informative. As mentioned before, we will basically edit the video. So we have about 4 hours video. We will edit it into parts and it will be available on Polymeris website. And we'll also share the slides on this website. There were a few questions, so we will put we will probably add a couple of slides on the questions and the answers to the questions. So I would like to thank the European Union for funding us, knowing that their views and opinions expressed here are not only that of the authors and do not reflect those of the European Union. I would also thank Nicolas at Polymeris for his help on this, for putting this webinar together, and thank them very much also for hosting videos later on for everybody to be able to access. So thank you again for your attendance, and I wish you a very good lunchtime. Bon appétit. Thanks.
Thank you.
Thank you, Anne.
Thank you.
Thank you.
Thank you.
Thank you.
Thank you.